This is problem 49 from chapter 17. In this problem, the cart's mass is 30 kilograms, and it is subject to a horizontal force of 90 newtons. We want to determine the tension in cord AB and the horizontal and vertical components of reaction on end C of the uniform 15 kilogram rod BC. So the rod has a mass of 15 kilograms. The cart has a mass of 30 kilograms. I think that when they say the cart, they mean everything on the cart except for rod BC. And we have a force here of 90 newtons. So we have 3 or 4 equations we can use, depending on how you look at it, for this problem. So we have Newton's second law in the x direction and the y direction, and we also have either equation 17.7 or equation 17.10, which we can use. In this problem, we're going to end up looking at rod BC as its own system. But the first thing that I want to do is find the acceleration of the cart and the rod, and I can do that by looking at the cart and the rod together. So this is for the system of the cart and everything on the cart. And the force that we have acting in the horizontal direction is 90 newtons. And then, of course, I have the force of gravity acting down on the cart and of the force from the surface acting on the wheels acting upward. But if I just look in the horizontal direction, I can say the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction. The only force I have acting in the x direction is the 90 Newton force, and the mass would be the mass of the cart plus the mass of the rod, so that is 30 plus 15 kilograms, and that's multiplied by the acceleration. And so I get the acceleration in the x direction is equal to 90 newtons divided by 30 plus 15 gives me 45 kilograms. So I get an acceleration of 2 meters per second in the x direction. And the wonderful thing about this is not only is that the acceleration of the cart, that is the acceleration of the rod also. So now I'm just going to look at the rod. And when I look at that rod, I have the acceleration already. Okay, so I have the 2 different equations I can use, which are equation 17.7 or equation 17.10. If I sum up the moments about the mass center, I'm going to have the forces that are acting at point C and the forces that are acting at point B, but I don't know the components of the forces, which is acting at point C. So instead, I'm going to sum up the moments about point C, and then I get rid of those unknown components. They don't appear in my equation. So I'm going to do the sum of the moments about point C. So I need, and that's equal to the sum of the kinetic moments about point C. So in order to do this, I'm going to draw a free body diagram. For the rod, and that's for the left-hand side of the equation, and I also draw a kinetic diagram, which is for the right-hand side of the equation. This is just for the rod, and from my picture here, I know that this angle is 30 degrees, and I have forces acting at point C. Now let's just say the x component is going in the positive x direction and the y component is going in the positive y direction. I prefer to do it this way, and then the sign that I get will tell me what direction that component is acting in. And then I have tension, which is acting along the chord in the direction that goes along the chord here, and this angle is 30 degrees. So I know that this angle here is 30 degrees. That's T, A, B. And because this angle is 30 degrees, that angle is also 30 degrees. So this is parallel with the rod. This is vertical, and both of those angles are 30 degrees. Okay, and then you have this angle here, like from here to here would be 30 also, so 30 plus 30 plus 30 adds up to 90. And then at the center of the rod, I have the force of gravity acting downwards, and this is the mass of the rod times G. Now let me make sure I have all my forces. That would be the non-contact force of gravity, and then I have a force for anything that's touching the rod, which would be the rope, and here at point C. So that's our free body diagram, and now we will do our kinetic diagram for the rod. And the rod is accelerating. We got the mass times the acceleration. So on our kinetic diagram, we do mass times acceleration, and if we had angular acceleration, we'd have to include the moment of inertia times angular acceleration, but the angular acceleration in this problem is 0. And because this angle is 30 degrees, this angle here is also 30 degrees, and the length of the rod is 1 meter. So this would be from here to here, this would be 0.5 meters. From here to here would be 0.5 meters, and from here to here would be 0.5 meters, but my drawing is a little too cluttered already, so I'm not gonna add that in. Okay, so then I do the sum of the moments about point C. So I need to know that if this is 30 degrees, then this angle here is 30 degrees. And when I do the sum of the moments about point C, remember that this comes from R, the vector R, which goes from here to here, crossed with your force here. And so you get the cosine component of MRG, which gives you a non-zero term for the cross product. And this distance from here to here is 0.5 meters. And then for the tension acting at the end of the rod, which is 1 meter away from point C, you do the cross product of the vector R, which goes from here to here. And when you cross that with the force of tension, you get this component here would be the cosine component, which would give you 0 when you do the cross product. So you have plus the tension times the sine component, and then the distance from here to here is 1 meter. This force of tension would cause rotation in the positive direction. This would cause rotation in the negative direction, so that should be negative. And then when we do the kinetic diagram here, we want the sum of the kinetic moments that's equal to the sum of the moments about point C. And so this is equal to the sum of the kinetic moments about point C. And we just have this one force here. And we have a cosine component which is acting this way and a sine component which is acting this way, and it's just the sine component that gives us a non-zero term for our cross product. That's R, which goes from here to here, crossed with this. So we have MRAX sine of 30 degrees, then the distance from here to here is 0.5, and that would cause rotation in the negative direction. So this is negative. I know what the mass of the rod is. I don't know what the tension is. I do know what the acceleration is, so I can solve this for the tension. And if I do that, I would bring this over to the other side and then divide by sine of 30 degrees. So this would be minus MRAX sine 30 degrees times 0.5. Then bring this over to the other side and it would be positive MRG cosine 30 degrees times 0.5 divided by sine of 30 degrees. The mass of the rod they gave us was 30 kilograms. And the acceleration we found here was 2 meters per second. And so you can put everything in and solve, and you should get the tension is 112.4 newtons. Okay, so we were asked to find the tension and also the horizontal and vertical components of reaction on end C. And what we've done so far, we used Newton's second law, but we used it for the cart and the rod together. And so now we're going to use Newton's second law for just the rod. We already have our free body diagram here, so we can use that and sum up the forces in the x direction for the rod and the sum of the forces in the x direction. That is Cx plus, this force does not have an x component. Tension does, and if this angle is 30 degrees, remember we said this angle is also 30 degrees, so the angle from here to here is 60 degrees. So that's plus TAB sine 60 degrees is equal to the mass of the rod, since we're doing the free body diagram for the rod now. So that's mass of the rod, which is 15 kilograms, times the acceleration, which is 2 meters per second. So that is 30 newtons. Why did I say this is 2 meters per second squared? Okay, so fixing the units, that gives us 30 newtons. And then we know what the tension is. We can plug that in there. When you solve for C, bring the tension over to this side. That's, well, times sine of 60 degrees is still going to be larger than the 30 that you have here. So for Cx, you're going to get negative 26.2 newtons, which means this component is acting that way. Okay, and if you knew that before and you wanted to say it was acting that way, then you should get something positive when you solve for that. And then we can do the sum of the forces in the y direction, which is equal to the mass times the acceleration in the y direction, but the acceleration in the y direction is equal to 0. So we can just say instead, upward forces are equal to downward forces if the sum of the forces in the y direction is equal to 0. So Cy is acting upward. We have a component of tension which is acting upward, which we could say, since this was the sine, that wasn't the sine, that was the cosine. This would be cosine of 30 degrees or sine of 60 degrees. So we could say plus TAB cosine of 60 degrees is equal to the mass of the rod times G, since that's acting downwards. Okay, and you know what the mass of the rod is, you know what tension is, and so you can plug everything in and you can solve for that on your own, and you should get Cy is equal to 49.81 newtons. And that concludes problem 49.